we continue section 9.5 to 9.7. Right, in this case, we will have the complex eigenvalues, and of course with that we have the complex eigenvectors to go with that as well. Right. So first, of course, we will find the eigenvalues. For that, we solve the equation determinant of A minus Ri identity matrix equal to 0. So determinant of this matrix where we subtract R on the diagonal equal to 0. Right, multiply -1 minus R times -3 minus R, subtract -2 plus 2 equal to 0. Multiply them out, -1 times -3 is 3. 3. All of them are negative, so multiply all will be positive. R and 3R, 4R plus R squared plus 2 equal to 0. So if R squared plus 4R plus 5 equal to 0. Well, let's see the graph. By the way, this expect to have the complex eigenvalues, so we should not have any x-intercept. X squared plus 4x plus 5. Right, the graph like that doesn't intercept the x-axis, so no x-intercept, no real 0. So that means we have to use quadratic formula or completion square. -4 plus or minus. Just write the formula first. -b plus b squared minus 4ac over 2a minus 4 plus or minus square root of b squared minus 4ac over 2a. So we have -4 plus or minus square root of 4 squared, 16 minus 20 is minus 4 over 2. So -4 plus or minus square root of -4 is 2i. Bring the negative outside is I. Square root of 4 is 2. Factor out 2. And cancel out the 2. So we have the solution is equal to what? -2 plus or minus I. Later on we can, actually that's just 1 with minus, 1 with plus. So in that case we can write this in the form of alpha I, alpha plus beta I. In the complex form, so we have alpha equal to -2 and beta is 1. Right, so keep this in mind in the later solution. Right, next we have the eigenvalues. Now the eigenvectors. Eigenvectors involve solving this system or this matrix equation. So we have the matrix negative, and then subtract the eigenvalues. The thing is, you can just pick any one of them. Just use the positive then. Just -2 plus I. Use that. We can use the minus or the plus. Doesn't matter. But subtract -2. Use the plus I. Right. And then 2. And the other one is 1. And then -3. Subtract the eigenvalues on the diagonal. Once again, you can choose either positive or negative eigenvalues. I mean negative or positive in the complex, in the imaginary part. So -1 plus 2 is 1 minus I, and then 2, and then -1, -3 minus to plus, so -1 plus minus I. Right. That's correct, but I just forgot the zeros. Just write that in the next line. 1 minus I, and 2 minus 1 minus 1 minus I, u1 u2 equal to 0 0. Now, usually we use the reduced row echelon form after this. But if we look at the first equation, if we do it correctly, when we have the eigenvalues, those two rows will be linearly dependent. So one row is the multiple of the other row. So essentially, we don't even need to use a reduced row echelon form when we have a 2 by 2. So we don't need to do reduced row echelon form for 2 by 2 because two rows are practically the same. So we can just take this row, right? And then we can say 1 minus I times u1 plus 2u2 equal to 0. In that case, you can solve for u1 in terms of u2 or u2 in terms of u1. By the way, the reason that I don't want to do the reduced row echelon form because the calculator doesn't do it. The calculator only do that on the real numbers. This is complex. It will not do it. Right. Also, I said if it's 2 by 2, if there's only 2 rows, we can just pick any row, and we only need one equation. Right. So we can solve for u1. So we can say 1 minus I u2 u1 is equal to -2 u2. So we can get u1 equal to -2 over 1 minus I. Even though it don't do the reduced row echelon form, but it can divide complex number. Hit mode, go to a plus bi, and select that. We have -2 divided by, open parentheses, 1 minus I is here. We have -1, -I. So if we will write it out, there's a u2. So we can write u as follow: u1, u2. u1 is -1, negative I. u1 times u2, sorry. Factor out the u2. Okay, don't skip that step, just -1 minus I, u2, and u2. Right? I'll just factor out u2. Or better yet, let's split this first. Factor out u2 and then split. -1 minus I and 1 times u2. Then we can split into -1 times 1 u2 plus -1 and 1 u2. There's an I somewhere, right? Sorry. We split this. It's better split like that. Split the real part and the imaginary part. So we have -1 and 1 times u2 plus -1 and 0 I u2. Factor out the I and we have -1 and 0. So bottom line is we're going to have an A and a B. The matrix A, the vector A and the vector B. So vector A is equal to -1 and 1, and vector B is equal to -1 and 0. So we have the eigenvalues and eigenvectors. It can be shown that it's just plus or minus later on. Yeah. So if we have the plus, if we have the -2 minus I, we end up with the plus. So the thing is, we only need to do one. Don't have to worry about plus or minus. So about finally, we go to the form where we have the complex solution. This is how we write the solution that is complex. So x1 is equal to E alpha t cosine beta t times matrix A, vector A minus E alpha t sine beta t times vector B. Of course, A and B are here, and alpha and beta are there. X2 is E alpha t sine beta t times A minus E alpha t sine beta t times B. Sorry, I just copy from what I have from that formula. If I copy correctly, right. And then we put all of that here. So we have E alpha -2 t cosine of beta t, beta is 1, and then A -1 and 1. By the way, this solution is different than what we have here, right? worry about that later. And then minus e to negative alpha t, which is negative 2 sine of t negative 1 and 0. And then x2 e to negative 2t sine of t negative 1 and 1 minus e to negative 2t cosine t negative 1 and 0. Of course, if we combine them, it's not going to be like this. However, remember, when we choose the eigenvalues and the eigenvector, we can choose u2 to be anything, right? In this case, I choose u2 to be 1. Now, if we choose u2 to be different values, it might work out better. So let's look at this. 1 minus I is equal to u1 plus 2u2. Now, if I moved 2u2 to the other side, notice that if we let u1 equal to 2, so why we do that? Because when we let u1 equal to 2, we have 1 minus I times 2 equal to minus 2u2. And cancel out the 2, move the negative to the other side, we have u2 is equal to 1, negative 1 plus I. And of course, we can write differently as u1 is 2, u1 is minus 1 plus I, which will we split into 2, and that is 2 and negative 1 plus I, 0 and 1. So this is another A and this is another B. We can use any matrix A or any matrix B, I mean vector A or vector B. If we use this set of A and B, this is the exact solution that we're going to have. Right. So that is the complex solution. Yeah. So like I said, the eigenvalues are unique, but eigenvectors, because we can choose u2 to be anything, so there will be more than one solution. Right. Next, repeated eigenvalues and generalized eigenvectors. Now, this is another case. Let's just go for eigenvalues first. Which is the equation A minus Ri determinant equal to 0. So determinant 3 minus 18, 2 minus 9 minus R equal to 0. So 3 minus R minus 9 minus R, subtract negative 36 plus 36 equal to 0. Right. So multiply it out. Negative 27 minus 3R plus 9R plus R squared plus 36 equal to 0. So combine like terms, R squared plus 6R plus 9 equal to 0. This one can be factors, R plus 3 times R plus 3. So if R equal to 3, negative 3, that is the double root. So, two equations, we expect to have two eigenvalues, but too bad we only have one here. So what can we do? Right, let's find eigenvectors which involves solving the equation A minus Ri times U equal to 0 vector, right? So 3 minus 18, 2 minus 9, minus R, which is negative 3. Right? U1, U2, 0, 0. Right, and so that gives us 0 and negative 18. And 2 and negative 12. Alright, make mistake, sorry, minus negative 3, so that should be plus. Sorry. Yeah. Notice that whatever we do here, we should have a matrix where one row is, they should be linearly dependent. For 2 by 2, one row is the multiple of the other. Right. This one's, let's do reduced row echelon form. Usually I do that just to simplify the numbers. I can just look at this number and work directly from it. Right, 6, negative 18, 2, and negative 6. Right, I said it just simplified the numbers. Don't really do much here. We can just pick any of these row and still work. Right, once again choose U2 to be arbitrary. And U1 minus 3U2, the first row equal to 0. So U1 is 3U2. So I will write the solution. U is equal to U1 and U2. U1 is 3U2. U2 is still U2. Choose U2 to be 1. We have an eigenvector of 3 and 1. U2, if we choose, equal to 1. Right. Now what? We have one eigenvalues, which is okay, but we have one eigenvectors. That is definitely not okay. So when we have values that is not, then we have to find the generalized eigenvectors. In this case, this is what we're going to find. Find another eigenvector v in this form. So this is called a generalized eigenvector. We have A minus Ri times V equal to U. If we only have one vector and we need another one, this is what we're going to do. A minus Ri, that's the same thing as 3 minus 18 minus 3, so plus 3. But this time times V, so V1, V2 equal to u. It's going to be 3 and 1. Alright, so give us what? 6, negative 18, 2, negative 6, v1, v2, 3 and 1. Let's do reduce row echelon form. Six, negative 18, 3, 2, negative 6, and 1. Right, if we do that, we're gonna have one, negative 3, 0, 0, v1, v2 equal to 1/2 and 0. It's not going to be 0 at the last column. So in this case, multiply the first row, we have v1 minus 3 v2 equal to 1/2. So we can say v1 is equal to 3 v2 plus 1/2. Now we could choose v2 to be anything. We can even choose v2 to be 0 if we want to. We choose v2 and v1 is 1/2, as long as the vector, the eigenvector, cannot be a 0 vector. Right. So we can choose v2 to be anything. I choose v2 to be 1. But if we write v as the solution, v1, v2, 3v2 plus 1/2, and v2. So we have 3 and 1 times v2. Of course, that 3 and 1 is that, and then plus 1/2 and 0. Yeah. So if we choose v2 to be anything, here I choose v2 to be 1, like that, could be anything. Choose v2 to be 1, so we have v equal to 3 plus 1/2, 7/2, and v2 is 1. And finally, we can write the solution. Okay. X1 is as before, so we say x1 is equal to e to the negative 3t, and eigenvector 1 is 3 and 1. Yeah, so the first vector is still the same as before, which is this. Now, but the second solution we have to write like this. X2 is equal to t e to the rt times u plus e to the rt times v. Yeah. So when we have the generalized eigenvector v, we have to write the solution like this, which is et e to the negative 3t, vector u is 3 and 1, plus e to the negative 3t, vector v is 7/2 and 1. Yeah. So x1 and x2. So that is where we have the generalized eigenvector. If you haven't taken different linear algebra, this might be overwhelmed. So on the final, I only ask you to know how to do the first case, how to find the eigenvalues, eigenvector. There's no repeated eigenvalues, no complex eigenvalues either. Yeah, so in that case, when we have the solution, then we'll just say x1 is e times eigenvalues times t eigenvector, x2 e eigenvalues times t e to the negative e to the eigenvalues t and then time eigenvector. Yeah, just x1, x2, x3. So once again, on the test, on the final, you only see this case number 3, this case here, where we have linearly independent eigenvectors. Right. So that is the end of 9.6. Now we go to 9.7, which is even more advanced than this. This is not in the linear algebra, but it's a lot more advanced. So now I just want to go over this. We will have the variation of parameters in the matrix form. So if we have x1, x2 all the way to xn fundamental set of solution, meaning they are solution, if I put them in columns, I have the matrix X. Then a particular solution of the system x equal to ax plus the function t. This function t make it non-homogeneous, and with that case the particular solution is equal to the vector in the matrix form. Particular solution is the matrix X times the inverse of matrix X times the function dt, and then we integrate. Right, here's an example. If we have initial value problem, then that we're going to do this. Right, here an example. If we solve this matrix equation, differential equation in the matrix form, so we find the eigenvalues, eigenvectors, and at the end we put in the solution. Xt fundamental set of solution is a matrix, and then find the inverse of it, end up with this, and particular solution is equal to the matrix times integral of the inverse times the f of t. So the matrix inverse f of t is input function, it's going to be that, and multiply that, you have 2 and negative 1, and finally that is particular solution. We're just going to add it to at the end. So this is a little bit advanced. Normally we have to work in the matrix form, find eigenvalues, eigenvectors, and then we have to solve for this, or this integral for the particular solution. This problem is simple, but we'll see we have a lot of work already. So if we have a 3 by 3, inverse of 3 by 3 is going to be a pain, especially that it is the matrix has the variable t in it. So finding the inverse is the problem, and then multiply by that. But it will just work in the matrix form. Right, I'm just going to put that section 9.7 like that, just to complete what we're supposed to cover for differential equation. But that's the end of what I want to cover for differential equation. That's 161 pages in total. And for one last time, thank you for watching.